start this afternoon's lectures. The first will be by Manfred Denker from Steiner. We'll be talking about the Toral automorphisms driven by continued fractions.
Okay, thank you very much, and thank you for the invitation. Actually, that's the first time I'm in the Hausdorff Institute, and I'm a little bit older, so despite the fact that I lived in this region here for quite some time. So when you asked me whether I could give a talk, then I thought the best thing is to talk about a little bit a work which is a little bit older, and actually it's incomplete work. It's joined with Gordin, who unfortunately died in 2015. And this is, the talk is on one of his main interests. And Gordin was interested in number theory and dynamics and probability theory, which you easily can see from his dissertation, which unfortunately is only in Russian, but it contains much of the ideas which later was published by Loyola and York. And what is best known from the dissertation is his criterion for the central limit theorem, and that's what's called the Gordin approach. And what I'm talking about here is some other idea, which I would say is a legacy of Gordin, that is about homoclinic transformations and homoclinic groups. Okay, so that's the introduction. And so the setup is quite simple. The standard thing for torus automorphism. So we take a matrix which is determinant 1 and integers in the integers, 2 by 2 matrices, and I define an example of a torus automorphism. And we always assume here that the matrix is hyperbolic, and then you get an hyperbolic torus automorphism, which will be basic example. Also, the first talk by Richard is motivated by this example. Okay. So what we are interested in is studying sequences of Toral automorphisms. So usually when you have a Toral automorphism, you take the iterations, and so the powers, and because it's an automorphism, you also take the inverse powers. So you have stable and unstable manifolds. But now if you take a sequence of automorphisms, there's a problem with such notation, a notion. So that will come up later, and Gordin's idea was a new dynamic concept which is also suitable to handle such things. Okay. So, unfortunately, when I wrote down the abstract, I was a little bit sleepy, so I didn't formulate it quite exactly as I should have done it. So let's do that now properly. So you take a rational number and a continued fraction expansion. Okay, so the fraction expansion is A1, A2, that's the notation. And then you have the conversions, the nth conversions, that's the Pn and Qn, integers, and the quotient approximates the irrational number exponentially fast. So you get a matrix where you put off diagonal 1 and 0 and an in the diagonal, so it gives you an automorphism, and that's a basic ingredient of the sequence of automorphisms you want to study. So you define recursively A0 the identity, and Mn an times Mn minus 1. That's an. Okay, so what you get then by induction, that the matrix Mn is just a matrix where the n's, n minus first, and the n's convergent is present. So that's the type of matrices we are interested in. So An is hyperbolic, of course, and so is this matrix Mn. What you have to do is you have to calculate the eigenvalues, and so what you do is the well-known recursion relations for the conversions, and then you find that the eigenvalues are this here. This is the expanding direction, that's the contracting direction. So if you take Mn, like this here, expressed as the An, so in the abstract I didn't write down that the matrix really were interested, or the concatenation of the matrix An. Okay, so we consider Tn to be the hyperbolic Toral automorphism defined by Mn. That's the notation. Okay. So okay. So what you will see in a few moments that the sequence Tn with n greater or equal to 0 will not be sufficient to handle our problem. It will shown. I will show in a minute that you can define a stable direction, but no proper unstable direction for this sequence. So what we are doing is we simulate the double infinite sequence of Toral automorphism. So we need to define the what you call the inverses. Okay, what you do is you take another irrational number, alpha minus, we let alpha plus is the first choice, what we had, and alpha minus another one.
Is there a typo for n for negative?
Right?
No, okay, no, sorry, excuse me.
Sorry.
No.
Okay. Oh, you have to speak a little bit louder. My hearing is not the best. Or you have to come forward. Okay, so if you do that, you denote these matrices by a minus 1, a minus 2. And then you can define a double-sided infinite sequence of Toral automorphism. So that's done here. So that's what you had before. A0 is the identity, and if you go backwards, A0, a minus 1, up to an, then you get, and you take the inverse, you get a sequence of Toral automorphisms in the past. Okay, so you have an interpretation in the hyperbolic plane. You fix alpha plus and alpha minus on the real line, and you draw the geodesic, and then you can interpret these sequences as approximants to the geodesic. Okay. If you want to do that, I think I explained that a little bit in the book on dynamic system I've written. Only for Germans because it's in German. Okay. So that's a sequence of Toral automorphism. And it makes perfectly sense to study the dynamic properties of that. Okay. So what we need, we want to formulate the theorem I want to prove. And you see this approach here, or this type of sequences, is pretty new. It originates in the discussion of Gordin with Jens Markloff, where they discuss the sequence of maps if you go from one fundamental fundamental domain to another one. Okay, that's another way of defining such sequences that are defined by dynamics. Okay, so what I want to show here is a weak limit law of conversions to the Poisson limit. That theory itself may not be so interesting, but it's more interesting the way how you prove it and the way how you handle these double infinite sequences. So, for formulating the theorem, we need the notion of exceptional points. An exceptional point is a point which is periodic, or fixed point, I should say, to be precise, for one of these matrices or Toral automorphisms. Okay. So then we need a definition, because you have a Poisson law, we call it Poisson regular, of sets Gn, measurable sets, with certain conditions here. For us, the conditions are not so important, but what you see is here it's a symmetric difference. So if you translate, then the measure of the symmetric difference is bounded by some power of the probability of Gn. So P is always the Lebesgue measure. So we have a measure for all the transformations. This here, the second condition here, means that the Gn is in some ball of radius Rn. Rn is going to 0. And the condition is, the essential condition is that the set Gn is large enough in measure with respect to the ball in which it lies. Okay, this remark is important because it tells you something about what type of sets you can take.
So you don't impose conditions on Rn? Do you impose conditions on Rn?
One?
Here.
It's here.
Do you impose conditions on the decay of Rn? The radius Rn?
Yeah.
Do you say anything about what it should behave?
Rn is just, it comes out that automatically it has to go to 0.
Yeah.
Or if you want, you can write your Rn goes to 0. Okay. Okay, so what is the theorem? Here's the theorem. So you take a sequence of sets, which is Poisson regular with all these conditions, and converging, shrinking to a non-exceptional point.
Can you give an example?
That is important because
Can you give an example of a Poisson regular and non-Poisson regular sequence?
yeah, for instance, you take eight balls, or let me just postpone it a little while for a second. Okay. I want to discuss that on the next slide, that question. So, then you take a sequence of integers, Sn, which go to infinity, and has a property that 2 times Sn plus 1 times the probability of Gn converges to some number positive. And then you take the sum from minus Sn plus 1 up to Sn minus 1 of the indicator composed with t to the k. And this is the number of visits of a point to the sets Gn up to time S of n. Okay. Then it converges weakly to Poisson rules parameter lambda. What it means is exactly this here. The Lebesgue measure of the points which have exactly p visits up to time S of n converges to e to the minus lambda lambda to the p with p factorial for p an integer, so positive integers. Okay, that's a typical Poisson limit theorem, which is known in elementary probability, and everybody who attended that class know that law and that type of theorem for Bernoulli variables. So, okay. So let's discuss it very shortly, what it means. So take p equals 1. This means you have up to time as of n, you have exactly one visit asymptotically. Then what is known, if you have a Poisson law, then the waiting time until you have that is exponential asymptotically. That's a standard thing, duality between exponential distribution and Poisson distribution. But here we have two-sided things, not one-sided. So if you define the waiting time as the smallest k, where tk is in Gn, and you can have 2 points, say +1 and -1. Okay? So it's not uniquely defined, but you still can look at the event where 2 of n is less or equal to t, and you intersect it with the event that the entry is unique. You only have 1 point. Say if you have 2, it's not permitted. Then 2n conditioned on the events Bn is an exponentially asymptotically exponential distributed. Okay? So that has to be changed against to the classical theorem or duality result. Okay, so you can connect that in the sense that you have these sets Gn, and what you want to have the asymptotic rate that you have the first entrance, or one entrance. And that is connected to the sweeping outer rate. This means you take a set, so for transformation, you take a set of positive measure, and then you iterate. If it's ergodic, the measure of the union will go to 1. So you can ask the question, what is the sweep out rate? Which means you take 1 minus that number. And the way how it converges to 1 gives you the exponential, or the asymptotic distribution. What is known that you can have sets with all possible limit distributions for the first entrance time. But here it shows that you have Poisson automatically. And a necessary condition and sufficient condition for that sweeping out rate, or this condition, conversions to the exponential law, is given by Chen in 2016. A necessary and sufficient condition. Okay. So that is one connection to many papers in the area where they study the first entrance time and the distribution. Mainly by Freitag, here the strongest results here. And now we come to your question, the discussion. What does it mean? So, first of all, if you have a Poisson limit law, what is known in literature is that the sets Gn are either balls in the Riemannian metric or the metric you're using, or they are symbolic balls. This means you take a Markov partition, and you take a cylinder set in a Markov partition, and you consider that as a ball. So the usual results on Poisson limit restrict themselves to these sets. Clearly, the condition I gave, these balls are contained in the condition here. because it was a condition that Gn is contained in the ball. And then you had an estimate of the measure of the ball against the measure of the set Gn. But if both sets are the same, you can estimate, of course. Okay? So, on the other hand, it tells you it has to be measurable, it has to be large. So you can apply it for convex sets and this type of thing. Okay? Does it answer your question?
Yes.
Okay. So it's not known, or any result where we really can characterize a set satisfy these conditions if and only if. Okay? That seems to be hard. The only result where arbitrary sets were given in the paper by myself and Gordin and Toral about 15 years ago. Okay. Second remark is the theorem here is about the non-stationary case. So Poisson limit theorems were known only in the dynamic case. So you have a new effect that you can have Poisson limit also in cases where you are non-stationary. That's important in dynamics because it should hold in dynamics as well in many situations, like you have in probability theory and Markov processes, there are a lot of Poisson limit theorems which are not stationary in the Markov processes. Okay. And the interesting thing is here the method of proof. So the method of proof usually uses either Sebastianov theorem, which is mimicking the classical Bernoulli case, or it using the transfer operator method. This transfer operator method, I think, was first used by Hirata beginning of the 90s. The Sebastianov theorem was used in the first paper on this type by Pittsburgh in 91 or so. Okay. So, and now you see if you use the transfer operator method, you have to deal with indicator functions, then you have to show that the indicator functions are elements of the Bonner space you're considering. So the homoclinic approach, which I will explain now, is adapted to general L2 functions. So it doesn't have that restriction. That's why it's here appropriate to use. Okay, so let me just check. So that's
can you
what I
go back
wanted
one
to say
moment?
here.
Can you go back one moment to the theorem you're discussing so we can... Can you put back the slide of your theorem so we can look at it one more moment?
Okay, so what I want to do in the rest of my time, I want to discuss a proof. This is more interesting about the theorem itself. Okay? Okay. So what you use here is something which is well known in probability, but hasn't been used except the paper with Gordin and Robert in the case of the Poisson distribution. This method is called the Chen Steiner method. It goes back to Steiner in '65, where he had a condition similar to that condition in the Chen theorem here for proving convergence to the normal rule, so the center limit theorem. So Gordin has given conditions for the central limit theorem using Stein's method in '93. So, and you can use exactly the same idea to prove the Poisson limit law by using the characteristic of Stein, which was 10 years later, of Chen, which was 10 years later than Stein. That's why I call it Chen-Stein method. Some people call it the Chen method here for the Poisson distribution. So it says if you have a sequence of random variables and lambda positive, and the sequence is z-values, integer values, then the necessary sufficient condition that you have the limit Poisson distribution is that for every bounded measurable phi, this equality holds. So it's a very simple thing, and this means you have to prove that relation here. Okay. So let me first explain how you do this here to a tractable expression. Okay, so there are lots of technically a little bit more or less complicated things which come from the conditions, what we have done, and they are elementary, so there's nothing involved here which is really of interest. So, what you first do is you reduce the problem of showing that this expression here, which is equal to this here, you just add this term here, and that goes to 0. So there is, where you put f and I, the indicator of Tn times Ti, okay, where the Fim means you fix I and you sum only over J, which is at least emptiest part from the I. And this here is just the indicator Tn composed with Tj, and that is part of the sum what we had to show. Okay, so we put and m equals 1, we just leave out the 1, and if m is equal to 0, we have just the Wn, which is, let me go back. Which is exactly this term here, the Wn. This here. That's the Wn. So it doesn't depend on I anymore. Okay. So you want to reduce it to that.
So
and how does it go?
So in the theorem, there is a sequence an which is fixed all over the theorem. The sequence an. At the beginning of the, you have a sequence an, and it's fixed.
Which an?
An. This is fixed all over. And,
Yeah.
and you don't see it in the theorem, so it's it doesn't depend on an of the story. It does not depend.
You see the Wn you have to compose with Tj.
Yeah, Tj, so it's inside,
Yeah.
but then the output does not seem to depend on an.
There are no hypotheses on
Exactly.
an.
There is no hypothesis on an. This is my question. It's a
Why
question.
the Tj's?
Yes, there are in Tj, but okay, there are no hypotheses on them.
Yeah.
Yeah, the general.
I think alpha plus and alpha minus, alpha plus and alpha minus have to be.
So that is exactly according to the Chen method, what you have to prove, that the Wn is the sum over 1Gn composed with T to the Ti. Okay. So that is what you have to estimate. So what you do is you make a little trick here, using that f and I is an indicator function. So when f and I is equal to 0, then the contribution in that sum here is 0 anyway, and if n equals 1, then we know that Wn is this here plus 1. Okay. So that's a trivial thing, but that's the trick how you estimate it. And then you just add and subtract terms. So what happens here is subtracting, adding, subtracting, adding. And then you have to estimate several term, and now you see, we don't have to go to the details here, that this term you can estimate, but this is right away by the general conditions, and this here can be estimated as well. So you're left over with this term here. Okay. And now you see what you can do is, instead of phi, you take phi of x plus 1. So we can delete this here, what you have to show. So we have to show that this here goes to 0. Okay? So this is exactly what was written here. And of course, the lambda you can replace by 2s plus 1 times p of gn by the condition that converges to lambda. Okay? So we do that here right away. Okay, so the further reduction is what I just said. You replace a phi by phi x plus 1. And then you decompose further into two terms by adding and subtracting. So we have here the w and I, where we leave out just the 1. And now you know when you have dependence, weak dependence, just a gap of 1 is not enough, you have to enlarge it. So you do that by introducing the w and in. You add it here and you subtract it here, or vice versa. And then you have to estimate this here by this here. Okay, the way how you do it, this here is left, so you have to make this here by that term plus the remainder. What you have to observe here, if you do estimate this as fi, and this here means that these two are different if sum of the f trace is equal to 1. So you can replace this indicator function, this function here, by the sum of the indicator function of the f trace. So you get the fi times f trace here. And that's why you get this term here. Now we are ready with the simplification of the expression to see what has to be proven. And there are two things here which has to be shown to go to 0. That's the first thing. And here the second one. So the first thing you would treat with the homoclinic Laplace operator. That is what I have to explain next. And the second thing is this here, and this is done by geometry of, in the classical case where you have one transformation, you use stable and unstable foliation to estimate that. Okay? In the sense that if you take the universal cover, then you can, so if you take the intersection of two sets, you will see that later, of some rectangle intersected with the iterate of the same rectangle, then you get stable and unstable directions, which are cut into small pieces or very long pieces. Okay. So the intersection will be very small sets, but a lot of them. You have to calculate the size of the small set and the number of pieces you get. Okay, but let's do that at the end. More important is to explain how to treat the first sort. So what you have seen is that the matrices Mn have, say, the positive integers, have eigenvalues which are proportional to these numbers. That is what you call the eigendirections of the, yeah, there should be a k here. Here, that's correct. Here it's a misprint. So the eigendirections are given by the conversions. And now you see that this here, in the stable direction, it converges to 0. So what it means is that in the stable direction, the direction of the different matrices converge to one fixed direction. In the unstable case, you can't say anything. That's what I said in the beginning. So the positive part defines a limiting stable direction. Okay. So also what you get is subgroups defined by the points which under iteration, forward iteration tk of x goes to 0. And you also can do that fixing n, and you take all points x with that relation. Where n equals 0, you get it back what you had in the beginning. Okay. So, that's the standard thing. So we also can do that for the Mn where n is negative. Okay. So when you do that with the matrices, then the stable direction for the inverse becomes the unstable for the whole sequence. By taking. Okay, so the unstable directions are given by the conversions of the alpha minus, and the unstable direction for the whole sequence will converge, similar as before, to the point direction 1 over alpha minus. Okay. So we get analogously the unstable subgroups gamma un. So that's the way how you treat it theoretically. So I've written down what it is again here. And these families are equivariant under these transformations here. So the nth homoclinic group is defined by all points which are in here and in here for fixed n. So that corresponds to the transversal the homoclinic points of the intersection of stable and unstable foliations in the classical case. So that's a free appealing group. And now you choose generators gamma 1 and gamma 2 of the homoclinic group, which is gamma 0, which means that t to the k x goes to 0 and as k goes to infinity, and t to the minus k x goes also to 0 for k to infinity. Okay. Now, what it means is that you have defined a particular subset of points in this space. And that gives you a hint why I think it's comparable to the transfer operator method. What you do in the transfer operator, you single out points first, given by the pre-images of points, which also classifies you the sequence of points, which has nice property. And as you saw in the first talk in the morning, these points have nice asymptotic properties. So here you have another set of points which you can use as approximations to other objects. And here we use it for handling this term in the Poisson limit theorem, what we have to do. Okay. So we have to define the plus operator. So what we have is the translation operators on the Toral. So here's something where Gordin got stuck. If you want to do similar things on arbitrary manifolds, you have difficulties with these things. Because it may not be well defined, only locally. Okay, so you have the unitary operator associated to the Tn, and also, so you have a family of operators, and then you can show that because of the definition that if G is in gamma in the homoclinic group, then UN H G UN star goes in identity in the strong operator topology. So, and also you can identify this here as the operator where you take Tpn plus n, the same n, and you apply it to gamma L for the two generators, L equals 1 and 2. So then you define your plus operator by this formula here. So plus operator because you have to find a name which is appealing. So you call it a plus operator, and once you have called it a plus operator, then of course you want a green formula. Okay? Otherwise it would not be justified. And in fact you have a green formula, so I can show you. Okay. So we have the Laplace operator, and first of all, let's make it more general, that definition. So you have an automorphism of a probability space, which means invertible transformation. You don't need any topology, it's just general. And you have also, of course, transformation is P preserving. P is no probability, not a back measure necessarily. And you have the unitary operator on the A2 space. Then you call a measure preserving transformation of the space or homoclinic, and the associated unitary operator, homoclinic operator, if you have exactly the condition you had before. So what you can do in general probability spaces, you can define what a homoclinic transformation is. The open problem is how to study the set of homoclinic transformation on the space. There is no work on that, although that's wide open. And more simple is if you only ask the question, what are the homoclinic operators? You can take that definition without the transformation order. Okay, so that's the general definition, and associated with that, a wide open problem. And that is actually what I call Gordin's legacy, because he was very interested in studying this question: what are the homoclinic structure on level spaces? I mean, on easiest way would be symbolic space. It shouldn't be so difficult, but in general, it's I have no idea how to tackle such a problem. I still have 5 minutes. It may be sufficient. So, what you have to know is that the Laplace operator is a closed symmetric form on L2, which means that the dense subspace in L2, 0. L2, 0 means all function is integral 0. And this means you take the Fourier extension on the L2 space, L2, 0, and then you have an inverse of that. So the inverse of the Laplace operator is well defined on all of L2, 0. So, and the thing you have to prove is that the Laplace operator has a spectral gap, which here is expressed in this form here. That is when you prove the transfer operator, it has a spectral gap, that you have equivalence statement here. So you prove it, and that was done by Gordin in 93. You take a character, and then it's a very simple proof for the Toral's automorphism, where you here use the dual map, and you work with the dual torus and the dual transformation, which comes from the dual matrix. And then the distance, because it's expanding, this distance here stays positive, and then you get everything, which is a consequence of expansiveness. Okay. So, and now you estimate the sum, and you do what I said before. Here, the gamma to the minus one is well defined. One function is integral 0. So here you have a function with integral 0, so you can apply it. And so if you take out here out as an inner product, here's a bracket missing, then you get exactly this here. Okay. So, and then you estimate this here by Cauchy-Schwarz, and using the inequality what we had. So it said that the inner product of delta of a function with another function is greater or equal to C. So what you have to do is you have to anyway. We have to turn it around somehow. I'm lost a little bit at the moment on how that works exactly. So you get the norm of the two functions, or the product here of that function, is bounded by c to the minus 1 times plus operator of these things. So you turn that around, and then you get the product, you use Cauchy-Schwarz, and you come to this here. And now you have to estimate the L2 norm of these things. And that is by using symmetric differences. And then you use the convergence in the stable unstable direction, where you get the, and that goes exponentially, that gives this factor, and this is the way how you do it. Square root of a half, because you have to estimate the norm here, so there's nothing serious in that formula. So you just do standard techniques here. So now we have to estimate the last term, and I'll make it very brief now. What you have to estimate is this term here. That's what you had before. So what you do is you take Gn is contained in a small rectangle. Where Ru and Su are along the stable and unstable directions. So it's a parallelogram, and then you do the standard trick. You estimate the difference or the covariance by the probability of the intersection. This function is 1 if and only if the point is in the intersection. So what you have to do is you have to estimate the image of a small rectangle under t to the I and t to the j. So you do that with the following lemma. You can estimate that this term, and in order to do that, that's what I said in the beginning. What you do is you take the parallelogram you get by shrinking the unstable direction with t to the minus k, and the stable one by t to the k, dk. And you do it, you have to do it for I and j, but you can do it simultaneously where I is equal to j, because it doesn't really matter in the estimate. So you get that probability, and then you have to count how many intersections or little pieces you have if you put it back. Yeah, that's near the cardinality of these intersections, and yes, that you estimate by the area including by the cover that I said before. So what you get is a constant times the length of tk rs times the length of tk ru in the universal cover, which is this here times this one. You estimate by the area of that, and then you get the length here. And then for the RS of the stable and RU of the unstable. So what you get is here, if you estimate this here, it's this is shrinking by the maximum eigenvalue to the minus 1. This is extending by the maximum eigenvalue. So these two factors cancel. What you get is the length of RS times the length of RU, which is constant times the P of R. You do that for the other case as well. So you estimate it by P of R, and then the condition is such that everything goes to 0. That's the technical situation. So here, we don't use Steiner's theorem. And then when you do higher dimension, you can do the same thing as here, using Steiner's theorems, because it allows you to calculate the Schwerpunkt of exponents separately on each direction. And you do the same thing on each direction, put it together with Steiner theorem. Thank you very much.
Are there any questions?
Good.
So, what,
Everything clear?
may I ask a question? So alpha minus and alpha plus should be different. alpha minus and alpha plus should be different, because otherwise you would have same state of the matter.
Of course.
But what about an? Does it doesn't have to be bounded. The an, they can
No.
be unbounded.
No.
And does it have an influence on convergence?
I don't know what the result will be if you do that.
Mm.
All what is needed is exponential decay, which you do.
Which is actually better when an is
Yeah.
large.
But you don't need any direct quantile property.
Okay.
Okay. But if you want to have different results, you may be using it, of course.
Right.
Okay, especially when, you see here it's interesting because here you use number theory to find something dynamically. If you're interested in the dynamics, usually you use dynamics to do things in number theory. Okay?
Right.
That was something I wanted to point out here.
Right. Yeah. In this conference in particular. Yeah. And you,
And how sensitive is it to this? So how sensitive is it to this type of continued fractions? What about like lambda continued fractions? If you change the system?
No,
it is?
what I think, you see, this is an example of the method in a non-stationary case. The paper appeared, I think, 2013 or so, and is just a sketch of proof. Okay? So one has to write out a complete proof along these lines, and if you do that, you can find out what else can be done. Okay? So that's
so if no
especially when you modify it to the hyperbolic plane.
So if no other questions, then let's thank the speaker again.